Tonight, we're going to attempt something that might seem impossible. We're going to count the stars. Not just the ones you can see from your backyard, not just the ones in our galaxy, but every single star that exists in the observable universe. And by the end of tonight, you're going to understand why this number is so incomprehensibly large that it fundamentally changes how you see reality itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Look up at the night sky on a clear evening, far from the light pollution of cities. Count the stars you can see. Go ahead, try it. You might count a few hundred, maybe a couple thousand if you have exceptional eyesight and perfect conditions. That number feels significant. It feels vast. But here's the thing that should fundamentally reshape your perception of the cosmos. Those few thousand stars you can see with your naked eye represent approximately 0.0000001% of the stars in the observable universe. The stars you can see, the ones that have inspired humanity's myths, guided our navigation, and sparked our curiosity for hundreds of thousands of years, are essentially a rounding error in the cosmic census. So, how many stars actually exist? The current scientific estimate places the number at approximately 200 billion trillion stars in the observable universe. That's a 2 followed by 23 zeros, 200 billion trillion individual nuclear furnaces, each one a sun, many of them larger and more powerful than our own, scattered across the incomprehensible expanse of space. But even that number, as staggeringly large as it is, doesn't quite capture the reality of what we're dealing with. Because to understand how many stars exist in the universe, we first need to understand what we mean by the universe. When astronomers talk about counting stars, they're specifically talking about the observable universe. That's the region of space from which light has had time to reach us since the Big Bang. The observable universe extends approximately 46.5 billion light-years in every direction from Earth. That's not 46.5 billion light-years total. That's the radius. The diameter of the observable universe is roughly 93 billion light-years. And yes, you might be wondering how the observable universe can be 93 billion light-years across if the universe is only 13.8 billion years old. Shouldn't light have only traveled 13.8 billion light-years in that time? The answer lies in the expansion of space itself. While light has been traveling toward us for 13.8 billion years, the space through which it's traveled has been expanding the entire time. The objects that emitted the light we're receiving now are much farther away than they were when that light began its journey. But here's something that should make your mind bend just a little bit. The observable universe is not the entire universe. It's just the portion we can see. The actual universe, the whole thing, might be infinite. We genuinely don't know. Current observations suggest the universe is either infinite or so large that the difference between its actual size and infinity is functionally meaningless to us. Which means the number of stars we're about to discuss, 200 billion trillion, is just the stars in the observable universe. The stars we could theoretically see if we had perfect telescopes and infinite time. Beyond the edge of the observable universe, there could be infinitely more stars. Stars we will never see because the light from them will never reach us due to the expansion of space. Stars that exist in a region of space so distant that they might as well be in a separate universe. So when we say there are 200 billion trillion stars in the universe, what we really mean is there are at least that many in the portion we can observe, and potentially infinitely more beyond that horizon. Keep that in mind as we explore this number, because it's going to get even more overwhelming. So, how do astronomers actually arrive at this number? How do you count 200 billion trillion of anything, let alone objects scattered across 93 billion light-years of space? Obviously, nobody is sitting there with a cosmic clicker tallying up stars one by one. The process is more clever than that, involving a combination of careful observation, statistical analysis, and elegant mathematical reasoning. It starts with counting galaxies. Galaxies are the basic organizational units of the universe, massive collections of stars, gas, dust, and dark matter bound together by gravity. Our own Milky Way galaxy is just one such collection, containing somewhere between 100 billion and 400 billion stars, depending on whose estimate you trust. To count galaxies, astronomers use something called a deep field survey. The most famous of these is the Hubble Deep Field, an image captured by the Hubble Space Telescope in 1995. Astronomers pointed Hubble at a tiny, seemingly empty patch of sky, a region about the size of a grain of sand held at arm's length, and let it stare at that spot for 10 consecutive days. The result was stunning. That tiny patch of empty sky contained approximately 3,000 galaxies, not 3,000 stars. 3,000 galaxies, each one containing billions or trillions of stars. Hubble's successor images, the Hubble Ultra Deep Field and later the Hubble Extreme Deep Field, revealed even more galaxies in similarly tiny patches of sky. The Extreme Deep Field, looking at a region about 1/32 millionth of the total sky, revealed about 5,500 galaxies in various stages of evolution. By scaling up from these sample regions to the entire sky, astronomers estimated there were approximately 100 billion to 200 billion galaxies in the observable universe. But then, in 2016, something changed. New analysis, incorporating data from Hubble and other telescopes, suggested the number was actually much higher. A team led by Christopher Consolis at the University of Nottingham concluded that the observable universe contains approximately 2 trillion galaxies, not 200 billion. That's 10 times more galaxies than previously thought. Most of these newly accounted for galaxies are small and distant, too faint to see even with our best telescopes, but statistical models suggest they must exist to account for the light we observe in the universe. So we've got 2 trillion galaxies. Now we need to figure out how many stars are in a typical galaxy. This is where things get tricky, because galaxies come in wildly different sizes. Our Milky Way, with its estimated 100 billion to 400 billion stars, is considered a large spiral galaxy, but some galaxies are much bigger. IC 10101, a supergiant elliptical galaxy, contains an estimated 100 trillion stars, more than 200 times as many as the Milky Way. On the other end of the spectrum, dwarf galaxies might contain only a few million stars. Segue 2, one of the smallest galaxies we know of, has about 1,000 stars. Yes, just 1,000 stars qualifies as a galaxy, though admittedly a very small one. To arrive at a total count, astronomers have to account for this distribution. They can't just multiply the number of galaxies by the number of stars in the Milky Way, because that would give an inaccurate result. Instead, they use statistical models based on observations of many different galaxies. They categorize galaxies by type, spiral, elliptical, irregular, and by size, then estimate the average number of stars in each category. The current consensus, based on these models, suggests there are roughly 100 billion stars per galaxy on average. Remember, that's an average. Some galaxies have far more, some have far less, but 100 billion is a reasonable middle ground for statistical purposes. So here's the math. 2 trillion galaxies times 100 billion stars per galaxy equals 200 billion trillion stars. 200 sextillion. That's our current best estimate for how many stars exist in the observable universe. But even as I say that number, I need to emphasize how much uncertainty exists in this calculation. We might be off by a factor of 2 or 3 in either direction. The number could be 100 billion trillion, or it could be 500 billion trillion. The uncertainty comes from multiple sources. We don't know exactly how many galaxies exist, especially small, faint ones beyond our detection capabilities. We don't know exactly how many stars are in each galaxy, because we can't count them individually. We don't know how many rogue stars exist between galaxies, untethered from any galactic home. And we don't know what we don't know. What types of stellar objects or configurations might exist that we haven't yet discovered. But despite this uncertainty, the order of magnitude is solid. Whether it's 100 billion trillion or 500 billion trillion, we're talking about a number that is so large it fundamentally defies human comprehension. Let's try to comprehend it anyway. Let's try to wrap our minds around 200 billion trillion stars. Start with something familiar. All the grains of sand on all the beaches on Earth. That's a number that comes up a lot when people try to illustrate vast quantities. So how many grains of sand are there on all of Earth's beaches? Estimates vary, but a commonly cited figure is approximately 7 quintillion 500 quadrillion grains. That's 7.5 followed by 18 zeros. 7.5 billion. It's a huge number. It feels incomprehensible. But here's the thing. There are more stars in the observable universe than grains of sand on all of Earth's beaches. About 27 times more, actually. If you gathered every grain of sand from every beach on the entire planet, you'd still need to find 26 more Earth's worth of sand to equal the number of stars. Let's try another comparison. Imagine you could count 1 star per second. Just point at a star, count it, move on. 1 per second seems reasonable, right? If you started counting stars at that rate, 1 per second, never stopping to sleep or eat or rest, how long would it take you to count all 200 billion trillion stars? 6.3 billion years. That's almost half the current age of the universe. You would have had to start counting shortly after the Earth formed and continue without pause until now to count every star in the observable universe, assuming you could somehow observe all of them from Earth, which you can't. But it gets even more absurd. Let's say, instead of counting stars yourself, you recruited helpers. Let's give you 1 helper for every person currently alive on Earth. About 8 billion people, all counting stars simultaneously, 1 per second each, never stopping. How long would it take? 793 million years. Nearly 800 million years of continuous counting by 8 billion people working simultaneously. That's longer than complex life has existed on Earth. You'd have to start this counting project back when the most advanced organisms were simple multicellular creatures, and you'd finish sometime around now. These comparisons aren't meant to be practical. Obviously, nobody is going to count stars one by one. The point is to illustrate just how vastly, incomprehensibly large this number is. 200 billion trillion is not just big. It's a number that exists in a realm beyond human intuition, beyond the scale of anything we encounter in daily life. Here's another way to think about it. If you wanted to visit 1 star per second, traveling instantaneously between them with no time for travel, it would take you 6.3 billion years to visit every star in the observable universe. But of course, you can't travel instantaneously. The fastest speed possible in the universe is the speed of light, approximately 186,000 miles per second. Even at that cosmic speed limit, traveling from star to star would take years, decades, centuries, or millennia, depending on the distance between them. The average distance between stars in our galaxy is about 5 light years. That means even if you could travel at light speed, it would take 5 years on average to get from one star to the next. To visit all 200 billion trillion stars at that pace would take approximately 1 quintillion years. That's 1 billion years. For reference, the current age of the universe is only 13.8 billion years. You would need the universe to live 72 million times longer than its current age to visit every star, assuming you could somehow travel at light speed and never stop. The scale becomes even more absurd when you consider that we can't travel at light speed. The fastest spacecraft humans have ever built is the Parker Solar Probe, which reached a top speed of about 430,000 miles per hour relative to the Sunday. That sounds fast, and it is by human standards, but it's only about 0.06% of the speed of light. At that speed, it would take about 75,000 years to reach the nearest star to our Sun, Proxima Centauri, which is only 4.24 light-years away. To visit all 200 billion trillion stars at that pace would take approximately 1.6 octillion years. That's 1.6 billion years. The number is so large it loses all meaning. These comparisons all point to the same conclusion. The number of stars in the observable universe is not just large, it's a number that exists on a scale fundamentally divorced from human experience. We can write it down, we can calculate with it, but we cannot truly comprehend it in any visceral, intuitive way. But let's zoom back down to something more tangible. Let's talk about what all these stars actually are. And more importantly, let's talk about where they come from and how they live and die. Because stars aren't eternal fixtures in the sky. They have births, they have lives, and they have deaths. Understanding this cycle helps us appreciate that the number we've been discussing isn't static. It's constantly changing as new stars are born and old stars die. Stars are born in stellar nurseries called molecular clouds. These are vast regions of space filled with hydrogen, gas, and cosmic dust, the raw materials from which stars are made. The gas is mostly primordial hydrogen and helium left over from the Big Bang itself, created in the first few minutes after the universe began. The dust consists of heavier elements, carbon, oxygen, silicon, iron, all created in previous generations of stars and scattered into space when those stars died. The largest molecular clouds can contain millions of times the mass of our Sun, spread across hundreds of light-years of space. To put that in perspective, a single molecular cloud could span the distance from our Sun to several of our nearest stellar neighbors. They're cold, incredibly cold, typically only 10 to 20 degrees above absolute zero. That's minus 440 to minus 420 degrees Fahrenheit. Colder than liquid nitrogen, colder than the surface of Pluto, colder than almost anywhere else in the universe, except the voids between galaxy clusters. They're dark, blocking the light from stars behind them and appearing as black voids against the starry background. The famous Horsehead Nebula in Orion is one such dark molecular cloud, its distinctive equine shape silhouetted against a brighter emission nebula behind it. And they're dense, at least by the standards of interstellar space, though they'd still qualify as a nearly perfect vacuum by Earth standards. The densest parts of a molecular cloud might contain 10,000 to 1 million molecules per cubic centimeter. That sounds like a lot, until you realize that Earth's atmosphere at sea level contains about 25 quintillion molecules per cubic centimeter. Even the densest molecular clouds are trillions of times less dense than the air you're breathing right now. And yet, by the standards of space, where the average density is about 1 atom per cubic centimeter, molecular clouds are incredibly dense. They're 10,000 to 1 million times denser than typical interstellar space. And that density, tiny as it seems to us, is enough for gravity to get a foothold. The process of star formation begins with some kind of disturbance that compresses part of the molecular cloud. Perhaps a nearby supernova explosion sends a shockwave rippling through the cloud, compressing the gas as it passes. Perhaps two molecular clouds collide as they orbit through the galaxy, their collision creating regions of higher density at the interface. Perhaps the spiral density wave of a galaxy's spiral arm compresses the cloud as the cloud passes through the arm. Whatever the cause, some region of the cloud becomes slightly denser than its surroundings. And gravity, weak but patient and relentless, begins to pull more material toward that dense region. This becomes a runaway process. More mass means stronger gravity. Stronger gravity pulls in even more mass. More mass means even stronger gravity. The positive feedback loop continues, accelerating over time. The dense region begins to collapse inward, contracting under its own weight. As it contracts, turbulence and rotation cause it to fragment into smaller clumps. Each clump then collapses independently. This is why stars typically form in clusters rather than individually. A single molecular cloud can spawn hundreds, thousands, or even millions of stars simultaneously, all forming from different fragments of the same parent cloud. The Orion molecular cloud, for instance, has produced over 3,000 stars in just the past few million years. Each collapsing fragment becomes what astronomers call a protostar. At this stage, it's not yet a true star. It's a dense ball of gas, growing hotter as it contracts, but not yet hot enough for nuclear fusion. The protostar is hidden deep within its dusty cocoon, invisible to optical telescopes. We can only see these objects using infrared and radio telescopes that can penetrate the dust. As the protostar contracts, gravitational potential energy converts to heat. Every atom falling inward gains kinetic energy. When it collides with other atoms at the center, that kinetic energy converts to thermal energy. The more the protostar contracts, the hotter its core becomes. The temperature climbs from hundreds of degrees to thousands, then tens of thousands, then millions. At 1,000,000 degrees, the protostar begins to glow brightly in infrared light. The protostar is also rotating, because any slight rotation in the original cloud fragment gets amplified as the protostar contracts. It's conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in. This rotation is crucial because it prevents all the material from falling directly onto the protostar. Instead, material forms a disk around the equator, an accretion disk of gas and dust spiraling slowly inward. This is the same type of disk that forms around black holes and around young planets, though on different scales. Material in the accretion disk gradually loses angular momentum through friction and magnetic interactions, allowing it to spiral inward and eventually fall onto the growing protostar. The protostar also launches jets from its magnetic poles, narrow beams of material shooting outward at hundreds of miles per second. These jets, powered by complex magnetic field interactions, help remove excess angular momentum from the system. Without the jets, too much angular momentum would build up and prevent material from falling onto the protostar. The protostar continues growing for hundreds of thousands of years, accreting material from its surrounding envelope and disk. Its mass increases. Its core temperature climbs higher and higher. And then, when the core reaches approximately 10 million degrees Kelvin, something extraordinary happens. Hydrogen fusion ignites. At these extreme temperatures and pressures, hydrogen nuclei, which are just single protons, move fast enough and are compressed densely enough to overcome their natural electrical repulsion. Protons are positively charged, and like charges, repel. Under normal circumstances, protons never get close enough to interact with each other. The electromagnetic force pushes them apart long before they can touch. But at 10 million degrees and the crushing pressures in a collapsing protostellar core, quantum mechanics provides a loophole. Even though the protons don't have enough energy to classically overcome the repulsive barrier, quantum tunneling allows them to occasionally pass through it. The probability is small for any individual interaction, but with trillions upon trillions of protons colliding every second, fusion happens at a steady rate. 4 hydrogen nuclei combine through a series of reactions called the proton-proton chain to form one helium nucleus. The helium nucleus has slightly less mass than the 4 hydrogen nuclei that created it. About 0.7% of the mass vanishes in the process. That mass doesn't disappear, it converts to energy, according to Einstein's famous equation, E equals mc squared. Even a tiny amount of mass converts to enormous energy when multiplied by the speed of light squared. The fusion of just 1 kilogram of hydrogen releases about 630 quadrillion joules. That's roughly equivalent to the energy in 15 million tons of TNT. The atomic bomb dropped on Hiroshima released about 63 trillion joules. 1 kilogram of fusing hydrogen releases 10,000 times as much energy. And a star like our Sun is fusing about 600 million tons of hydrogen into helium every single second. That's the mass of about 40,000 Empire State Buildings converted to pure energy every second. The Sun has been doing this for 4.6 billion years and will continue for another 5 billion years. This energy, radiating outward from the core, creates pressure that pushes outward. That outward pressure perfectly balances the inward pull of gravity. The protostar reaches equilibrium. Gravity trying to crush it inward is balanced by radiation pressure pushing outward. The protostar is now a star. It settles onto what astronomers call the main sequence, a long period of stable hydrogen burning that will last for most of the star's lifetime. Our Sun has been in this equilibrium state for 4.6 billion years and will remain in it for another 5 billion years. During all that time, it's been maintaining a perfect balance. Any slight perturbation is self-correcting through negative feedback. If fusion temporarily produces a bit more energy, the core heats up slightly and expands. The expansion reduces the core density and pressure, which slows the fusion rate back down. If fusion temporarily slows, the core cools slightly and contracts. The contraction increases density and pressure, speeding fusion back up. This automatic thermostat keeps stars stable for billions of years. But not all stars form at the same rate or in the same way. Star formation happens in bursts, in localized regions where conditions are just right. The Orion Nebula, one of the most studied star-forming regions in the galaxy, gives us a window into this process. It's located about 1,344 light-years away, close enough that we can study it in extraordinary detail. To the naked eye, it appears as a fuzzy patch in Orion's sword, just below the 3 stars of Orion's belt. Through a telescope, it resolves into a complex tapestry of glowing gas, dark dust lanes, and brilliant young stars. The nebula is only about 24 light-years across, tiny by galactic standards, and yet it's actively producing hundreds of new stars right now as we speak. At the heart of the nebula is the trapezium cluster, a group of several very hot, young O-type and B-type stars. These stars, only a few million years old, have already cleared away much of their dusty cocoons. They're so luminous that their ultraviolet radiation ionizes the surrounding gas, causing the entire nebula to glow. Behind them, still hidden in thick dust clouds, are hundreds of protostars in various stages of formation. Some are still gathering mass, slowly growing as material falls onto them. Others have nearly reached the point where fusion will ignite. Still others have just recently become true stars. Using infrared telescopes like the James Webb Space Telescope, we can peer through the dust and watch stars being born in real time. Over the next few million years, the most massive stars in the trapezium will live out their brief lives and explode as supernovae. Their explosions will blow away the remaining gas and dust, halting further star formation in the region. The surviving stars will form an open cluster that will gradually disperse over tens or hundreds of millions of years. This cycle, from molecular cloud to star cluster to dispersed stellar population, is happening in thousands of locations across every galaxy in the universe. Every second, somewhere in the observable universe, about 100,000 stars are being born, 100,000 new stellar furnaces igniting for the first time, and every second, old stars are dying, completing the cycle, because stars don't last forever. The same fusion that powers them eventually leads to their demise. The fate of a star depends almost entirely on one factor: its mass. Massive stars, more than 8 times the Sun's mass, live fast and die violently. They burn through their hydrogen fuel in only a few million years, despite having more fuel than smaller stars. The reason is counterintuitive. More massive stars have stronger gravity, which requires higher core temperatures and pressures to maintain equilibrium, and those higher temperatures drive fusion at exponentially faster rates. A star 20 times the Sun's mass might exhaust its hydrogen in only 5 million years. A star 50 times the Sun's mass might last only 2 million years. When a massive star runs out of hydrogen in its core, the core contracts and heats up until it reaches 100 million degrees. At that temperature, helium fusion becomes possible. 3 helium nuclei fuse to form carbon through a process called the triple alpha reaction. This buys the star more time, but not much. Helium fusion lasts only a few 100,000 years in a massive star. Then the core contracts again, heats up further, and carbon fusion begins, creating oxygen and neon. This lasts only a few thousand years. Then neon fusion, lasting less than a year. Then oxygen fusion, lasting a few months. Finally, silicon fusion, producing iron. This final stage lasts about 1 day. One single day, and the star reaches the end of the line. Iron is the most stable element in the universe. Fusing iron doesn't release energy, it consumes it. There's no fusion reaction involving iron that can support the star. So the iron core just sits there, growing larger as the outer layers continue fusing lighter elements and adding to it. The core is supported only by electron degeneracy pressure, a quantum mechanical effect, but that can only support so much mass. When the iron core reaches about 1.4 solar masses, electron degeneracy pressure fails. The core collapses. In less than 1 second, a stellar core the size of Earth collapses to a ball only 12 miles across. The density becomes so extreme that electrons are crushed into protons, forming neutrons. When the collapsing core reaches nuclear density, neutron degeneracy pressure finally stops the collapse. The infalling material rebounds, creating a shockwave that blows the star apart. This is a supernova, one of the most violent events in the universe. In a few seconds, the supernova releases as much energy as the star produced in its entire multi-million-year life. For a few weeks, it can outshine an entire galaxy of hundreds of billions of stars. The explosion flings the star's outer layers into space at tens of thousands of miles per second. These layers, enriched with heavy elements created during the star's life, spread into the interstellar medium. They'll mix with hydrogen and helium and eventually form new stars. Those new stars will have more heavy elements than their predecessors. This is how the universe becomes chemically enriched over time. Every element heavier than helium was created in stars. The carbon in your body, the oxygen you breathe, the calcium in your bones, all were forged in stellar cores and scattered by supernovae. you are literally made of stardust. Because when we say there are 200 billion trillion stars, we're not talking about 200 billion trillion identical objects. Stars come in a stunning variety of sizes, colors, temperatures, and lifespans. Understanding this diversity helps us appreciate not just how many stars there are, but what an incredible range of phenomena exists in the universe. Stars are classified primarily by their temperature, which correlates with their color and size. The classification system, developed in the early 20th century, uses letters that seem random at first: O, B, A, F, G, K, and M. But there's a historical reason for the seemingly arbitrary order. The letters were originally assigned in the 1800s, based on the strength of hydrogen absorption lines in stellar spectra. Astronomers labeled stars with the strongest hydrogen lines as type A, the next strongest as type B, and so on. Later, when they understood that temperature, not just hydrogen lines, was the key factor, they rearranged the sequence by temperature. That's why the letters are out of order. The mnemonic most astronomy students learn is, "Oh, be a fine girl, kiss me," though more modern versions exist. O-type stars are the hottest and rarest, with surface temperatures exceeding 30,000 Kelvin. That's about 54,000 degrees Fahrenheit. Hot enough to melt any known material instantly. Hot enough that their surfaces glow blue-white, emitting enormous amounts of ultraviolet radiation. These stars are absolutely massive, typically more than 16 times the mass of our Sun, often much more. The most massive O-type stars can exceed 100 times the Sun's mass. They burn through their fuel so quickly that they live only a few million years, a cosmic eye blink. They're so rare that they make up less than 0.0003% of all stars in the Milky Way. Out of the Milky Way's 400 billion stars, there are only about 100,000 O-type stars. That sounds like a lot, but it's an infinitesimal fraction. Out of the universe's 200 billion trillion stars, there are approximately 600 quadrillion O-type stars. 600,000 billion stars, which is enormous in absolute terms, but represents less than 1 in 300 million stars. Despite their rarity, O-type stars are crucial to galactic evolution. They produce most of the ultraviolet radiation that ionizes interstellar gas, creating the beautiful emission nebulae we observe. They have powerful stellar winds that blow away gas from star-forming regions, and when they die, they explode as supernovae, scattering heavy elements and triggering new rounds of star formation. The brightest star in the Carina Nebula, Eta Carinae, is a massive O-type star system that's extremely unstable. It's ejected more than 10 solar masses of material in eruptions over the past few centuries. It will almost certainly explode as a supernova within the next million years, possibly much sooner. B-type stars are also very hot, with temperatures between 10,000 and 30,000 Kelvin. They appear blue-white and are still quite massive, typically between 2 and 16 times the Sun's mass. They're more common than O-type stars, but still relatively rare, making up about 0.13% of stars in our galaxy. Rigel, the bright blue-white star marking Orion's left foot, is a B-type supergiant. Despite being about 860 light-years away, it's one of the brightest stars in Earth's night sky. It's about 120,000 times more luminous than our Sunday. If you replace the Sun with Rigel, Earth would be vaporized almost instantly from the intense radiation. Spica in Virgo is another famous B-type star, actually a close binary system of 2 B-type stars orbiting each other every 4 days. A-type stars have temperatures between 7,500 and 10,000 Kelvin and appear white or blue-white. These are the stars that dominate the apparent brightness of many young star clusters. Sirius, the brightest star in Earth's night sky, is an A-type star. It's about twice the mass of the Sun and about 25 times more luminous. It's only 8.6 light-years away, which is part of why it appears so bright. Actually, Sirius is a binary system. The bright star we see is Sirius A, an A-type main sequence star. Orbiting it is Sirius B, a white dwarf that's the remnant of a star that exhausted its fuel and died. Vega in Lyra, another very bright star, is also an A-type star. It's about 40 times more luminous than the Sun and is surrounded by a debris disk, possibly indicating the presence of planets. F-type stars have temperatures between 6,000 and 7,500 Kelvin and appear white. Procyon, the eighth brightest star in Earth's sky, is an F-type subgiant. Like Sirius, Procyon is also a binary system with a white dwarf companion. F-type stars make up about 3% of all stars. Then we come to G-type stars, and this is where things get personally relevant. Our Sun is a G-type star, specifically classified as G2V. The G indicates its spectral type based on temperature. The 2 is a subclass, indicating it's on the cooler end of the G range. The V, from the Roman numeral for 5, means it's a main sequence star, currently burning hydrogen in its core. G-type stars have surface temperatures between 5,200 and 6,000 Kelvin. They appear yellow-white, though our eyes perceive the Sun as yellow due to atmospheric scattering. In space, the Sun would appear white. G-type stars make up about 7.6% of all stars. That means out of 200 billion trillion stars, approximately 15 billion trillion are similar to our Sunday Tabe, 15 quadrillion sun-like stars scattered across the cosmos, each one potentially hosting planets. Some of those planets might be in the habitable zone. Some might harbor life. Alpha Centauri, a part of our nearest stellar neighbor system, is a G-type star, slightly more massive than the Sunday. Tau Ceti, about 12 light-years away, is another nearby G-type star that has attracted interest in the search for habitable planets. K-type stars are cooler still, between 3,700 and 5,200 Kelvin, appearing orange. They're smaller and less massive than the Sun, typically 40 to 80% of the Sun's mass. But they're more common, making up about 12% of all stars. K-type stars are particularly interesting in the search for life because they're stable and long-lived. They live longer than G-type stars, giving planets more time for life to evolve. But they're not as prone to violent flares as M-type red dwarfs. Alpha Centauri b, the other star in the Alpha Centauri binary, is a K-type star. Epsilon Eridani, about 10.5 light-years away, is a young K-type star with a confirmed debris disk and possible planets. And finally, M-type stars, the most common type of star in the entire universe. These red dwarfs have surface temperatures below 3,700 Kelvin and appear red or orange-red. They're small, typically less than half the Sun's mass. The smallest can be as little as 8% of the Sun's mass, barely massive enough to sustain fusion. They're dim, producing only a tiny fraction of the Sun's luminosity. Proxima Centauri, our nearest stellar neighbor at 4.24 light-years away, is an M-type red dwarf. It's only about 12% of the Sun's mass and produces only 0.17% of the Sun's luminosity. If you replace the Sun with Proxima Centauri, Earth would freeze solid within weeks. The planet would be plunged into permanent twilight, receiving barely enough light to see by. Despite being so dim, M-type stars make up approximately 76% of all stars in the Milky Way. 3 out of every 4 stars in existence are these small, cool, dim, red dwarfs. This has profound implications for our understanding of the universe. When we picture stars, we tend to think of bright, impressive objects like the Sun or Sirius or Betelgeuse. But the typical star, the median star in the universe, is actually a faint red ember, a star so dim it's invisible to the naked eye from more than a few dozen light-years away. Proxima Centauri is the nearest star to us, and yet it's completely invisible without a telescope. This distribution means that when we look at the night sky, we're seeing a heavily biased sample. The bright stars that dominate our view are the rare exceptions. The O, B, and A-type stars that make up less than 1% of the total stellar population. The vast majority of stars are invisible to us unless they happen to be very close. If 3/4 of all stars are red dwarfs, that means out of 200 billion trillion stars, approximately 150 billion trillion are these long-lived red embers. 150 billion trillion red dwarfs, most burning steadily for trillions of years. And paradoxically, these faint stars might be the most important for life. Their longevity gives planets orbiting them immense amounts of time for evolution. Earth has had complex life for only about 600 million years. Red dwarf planets could have trillions of years. And because red dwarfs are so common, there are vastly more potential habitable planets around them than around Sun-like stars. The nearest potentially habitable exoplanet discovered so far, Proxima Centauri b, orbits a red dwarf. In the search for life beyond Earth, these dim red stars might be our best hope. O-type stars are the hottest and rarest, with surface temperatures exceeding 30,000 Kelvin. That's about 54,000 degrees Fahrenheit. They appear blue or blue-white to our eyes and are absolutely massive, typically more than 16 times the mass of our Sunday. These stellar giants are rare, making up less than 0.0003% of all stars in the Milky Way. Despite their rarity, they're incredibly important to the universe's evolution because they burn through their fuel quickly and explode as supernovae, scattering heavy elements into space. B-type stars are also quite hot, with temperatures between 10,000 and 30,000 Kelvin. They appear blue-white and are still quite massive, typically between 2 and 16 times the Sun's mass. They're more common than O-type stars but still relatively rare, making up about 0.13% of stars in our galaxy. A-type stars, with temperatures between 7,500 and 10,000 Kelvin, appear white or blue-white. Our Sun's neighbor Sirius, the brightest star in Earth's night sky, is an A-type star. These stars make up about 0.6% of the stellar population. F-type stars have temperatures between 6,000 and 7,500 Kelvin and appear white. They make up about 3% of stars. Then we come to G-type stars, and this is where things get personally relevant. Our Sun is a G-type star. These stars have surface temperatures between 5,200 and 6,000 Kelvin and appear yellow-white. They make up about 7.6% of all stars. K-type stars are cooler still, between 3,700 and 5,200 Kelvin, appearing orange. They're more common, making up about 12% of all stars. And finally, M-type stars, the most common type of star in the universe. These red dwarfs have surface temperatures below 3,700 Kelvin and appear red or orange-red. They make up approximately 76% of all stars in the Milky Way. Think about that for a moment. 3 out of every 4 stars in the universe are small, cool, red dwarfs. When we picture stars, we often think of bright, luminous objects like our Sunday. But the typical star in the universe is actually much smaller and dimmer than our Sun, a faint red ember that could burn for trillions of years. This distribution has profound implications for the total count. If 3/4 of all stars are red dwarfs, that means out of our 200 billion trillion stars, approximately 150 billion trillion are these small, dim, long-lived stars. Most of them are so faint that we can't see them individually, even with our best telescopes, unless they're relatively nearby. The nearest red dwarf, Proxima Centauri, is only 4.24 light-years away, and yet it's completely invisible to the naked eye. You need a telescope to see it at all. This means when we look out at the night sky, we're seeing a heavily biased sample. The bright stars that dominate our view are the rare, massive, luminous stars, the O, B, and A types that make up less than 1% of the total stellar population. The vast majority of stars, those dim red dwarfs, are essentially invisible to us unless they happen to be very close. So when you look at the night sky and see thousands of stars, remember that you're seeing the universe's rare exceptions, its largest and brightest stellar citizens. The typical star, the one representing the vast majority of those 200 billion trillion, is a faint red coal you'll never see without significant optical aid. But stars differ in more than just temperature and color. They also vary enormously in size. The smallest stars, those red dwarfs we just discussed, can be as small as 8% of the Sun's mass. Below that threshold, there's not enough mass to sustain hydrogen fusion, and you get a brown dwarf instead, a failed star that never quite ignited. The largest known stars, on the other hand, are almost incomprehensibly massive. Stephenson 2-18, currently considered one of the largest known stars, has a radius approximately 2,150 times that of our Sunday. If you placed it at the center of our solar system, its surface would extend beyond the orbit of Saturn. Saturn would be inside the star. The volume of Stephenson 2-18 is approximately 10 billion times the volume of our Sunday. 10 billion suns could fit inside it. And yet, despite its enormous size, Stephenson 2-18 has only about 16 to 20 times the mass of our Sunday. That's because it's a red supergiant, a dying star that has expanded to enormous size but is actually quite diffuse. Its outer layers are so tenuous that they're closer to a vacuum than anything we'd recognize as solid matter. UY Scuti, another red supergiant, is also a contender for the largest known star. Its radius is uncertain, but estimates place it at roughly 1,700 times the Sun's radius. Again, if you put it where our Sun is, it would engulf everything out to Jupiter's orbit. These hypergiant stars are incredibly rare. Out of those 200 billion trillion stars, only a tiny fraction, perhaps a few billion at most, achieve these truly monstrous proportions. Most stars, remember, are small red dwarfs. But the existence of these giants adds to the stunning diversity of the stellar population. Stars also vary in their luminosity, the total amount of energy they emit. Luminosity depends on both size and temperature, so the most luminous stars are both hot and large. R136A1, a star in the Large Magellanic Cloud, is one of the most luminous stars known, emitting approximately 8.7 million times more energy than our Sunday. If you placed R136A1 at the center of our solar system, the Earth would be vaporized almost instantly. Its light would be so intense that Earth's oceans would boil away in seconds, the atmosphere would be stripped off, and the surface rock would melt into lava. On the other end of the spectrum, the faintest stars emit only about 0.0001 times the Sun's luminosity. These dim red dwarfs are barely glowing at all compared to more massive stars. The luminosity range of stars spans about 100 billion-fold. The brightest stars are 100 billion times more luminous than the dimmest stars. That range is staggering. It would be like comparing a candle to a nuclear bomb, except the actual range is much, much larger. This diversity means that when we talk about 200 billion trillion stars, we're talking about an incredible variety of objects. tiny red embers burning for trillions of years. Blue supergiants blazing with unimaginable intensity, but burning out in a few million years. Yellow dwarfs like our Sun, stable and steady for billions of years. Dying red giants expanding to swallow their planets. Hypergiants so large they defy intuition. Each one is a nuclear furnace, a ball of plasma held together by gravity and powered by fusion. Each one is unique in its exact properties, its specific history, its ultimate fate. And there are 200 billion trillion of them. Now, let's talk about where all these stars are, because they're not distributed evenly throughout space. Stars cluster together in structures of increasing scale, from binary pairs to galaxies to galactic superclusters. The smallest stellar groupings are binary and multiple star systems. It turns out that most stars, perhaps 85% of them, are not solitary like our Sunday. They exist in binary pairs, or even larger multiple systems, where two or more stars orbit their common center of mass. Alpha Centauri, the nearest star system to our Sun, is actually a triple star system. It contains Alpha Centauri A and Alpha Centauri B, two Sun-like stars orbiting each other, along with Proxima Centauri, a red dwarf that orbits the pair at a much greater distance. Some systems contain even more stars. Castor, visible as a single point of light to the naked eye, is actually a sextuple star system, 6 stars gravitationally bound together in a complex orbital dance. If 85% of stars exist in multiple systems, that means out of our 200 billion trillion stars, approximately 170 billion trillion are part of binary or multiple star systems. Only about 30 billion trillion stars, still an enormous number, are truly solitary like our Sunday. This has implications for planets and potentially for life. Planets in binary star systems can have complex, chaotic orbits, with 2 suns in their sky, creating wildly variable amounts of heat and light. Some configurations are stable, with planets orbiting far enough from both stars to maintain regular conditions. Others are dynamically unstable, with planets eventually being ejected from the system or falling into one of the stars. Stars also cluster together on larger scales. Open clusters are loose collections of a few hundred to a few thousand stars that form together from the same giant molecular cloud. They're relatively young and will eventually disperse as their stars drift apart over millions of years. The Pleiades, also known as the Seven Sisters, is a famous open cluster visible from Earth. It contains over 1,000 stars, all born from the same cloud of gas and dust about 100 million years ago. Globular clusters are much larger and more tightly packed. These are spherical collections of tens of thousands to millions of stars, all bound together in a dense ball by gravity. The stars in globular clusters are typically very old. Some of the oldest stars in the universe, formed over 12 billion years ago when the universe was young. M13, the Great Globular Cluster in Hercules, contains approximately 300,000 stars in a region about 145 light-years across. At its core, stars are packed so densely that they're separated by mere light weeks or even light days, compared to the light-years that separate stars in our neighborhood. If you lived on a planet in the core of a globular cluster, your night sky would contain thousands of bright stars, and you would never experience true darkness. The Milky Way has about 150 known globular clusters orbiting it, and likely many more we haven't discovered yet. If each contains an average of 100,000 stars, that's about 15 million stars in globular clusters in our galaxy alone. Extrapolate that to all 2 trillion galaxies, accounting for the fact that larger galaxies have more globular clusters, and you get approximately 30 quadrillion stars in globular clusters throughout the observable universe. That's 30 million billion stars, which sounds enormous until you remember It's only about 0.015% of the total stellar population. Most stars don't live in globular clusters. Most live in galaxies. And galaxies themselves come in different types, each with different numbers and distributions of stars. Spiral galaxies, like our Milky Way, have a distinctive shape with arms spiraling out from a central bulge. They contain significant amounts of gas and dust, so they're actively forming new stars. The arms are brighter than the spaces between them because they contain both young, luminous stars and the nebulae where stars are being born. Our Sun orbits in one of the Milky Way's spiral arms, about 26,000 light-years from the galactic center. It takes approximately 225 million years for the Sun to complete one orbit around the galaxy. In the entire history of the Earth, our planet has only completed about 20 orbits around the Milky Way. Dinosaurs walked the Earth in a different part of the galaxy than where we are now. Elliptical galaxies are more rounded and lack the spiral structure. They contain very little gas and dust, so they're not actively forming many new stars. Instead, they're populated mostly by old, red stars. The largest galaxies in the universe are elliptical galaxies, massive collections of trillions of stars that formed through the merger of multiple smaller galaxies. IC 10101, which we mentioned earlier, is a giant elliptical galaxy containing approximately 100 trillion stars. To put that in perspective, that's more stars than there are cells in about 100,000 human bodies. One single galaxy contains that many stars. Irregular galaxies don't fit neatly into either category. They lack a distinct structure, often because they've been disrupted by gravitational interactions with other galaxies. The large and small Magellanic Clouds, visible from the southern hemisphere, are irregular galaxies that orbit the Milky Way. They contain billions of stars and are slowly being torn apart by the Milky Way's gravity. Eventually, over hundreds of millions or billions of years, they'll merge with the Milky Way, adding their stars to ours. And then there are dwarf galaxies, the runts of the galactic family. These small galaxies can contain as few as 1,000 stars, though most have millions or billions. They're the most common type of galaxy in the universe, far outnumbering larger galaxies like the Milky Way. But because they're so faint, they're difficult to detect unless they're relatively nearby. The Milky Way has at least 50 known dwarf galaxies orbiting it, and probably hundreds more that are too faint to see. Throughout the observable universe, dwarf galaxies likely outnumber large galaxies by at least 10 to 1. But despite being more numerous, they don't contain as many stars. If an average dwarf galaxy has 10 million stars and an average large galaxy has 100 billion stars, each large galaxy contains 10,000 times as many stars as each dwarf galaxy. So even though dwarf galaxies are more common, most of the universe's stars reside in large galaxies. This distribution affects how we count stars. When astronomers estimate there are 2 trillion galaxies, they're including everything from giant ellipticals with 100 trillion stars down to tiny dwarfs with only thousands. The average of 100 billion stars per galaxy accounts for this distribution, weighted toward the fact that while dwarf galaxies are common, they don't contribute many stars to the total. But here's something that adds another layer of complexity. Not all stars live in galaxies. Some stars exist in the intergalactic medium, the vast empty spaces between galaxies. These are called intracluster stars or intergalactic stars, and their existence was only confirmed relatively recently. How do stars end up floating in intergalactic space? The answer is galactic interactions. When galaxies pass close to each other or collide, their gravitational fields can strip stars from the outer regions and fling them into the void. It's like a gravitational slingshot. A star that was once part of a galaxy suddenly finds itself alone, drifting through intergalactic space with no galactic home. These rogue stars are difficult to detect because they're isolated and faint. We can't see individual rogue stars at cosmic distances. Instead, astronomers detect them by observing a faint glow in galaxy clusters that comes from stars not clearly associated with any particular galaxy. By measuring this intra-cluster light, astronomers can estimate how many stars are floating free. Current estimates suggest that between 10 and 50% of all stars in galaxy clusters might be intra-cluster stars, untethered from any galaxy. If we apply this to the universe as a whole, accounting for the fact that not all galaxies are in clusters, we might have tens of trillions of rogue stars wandering the intergalactic void. That could add 5 to 20 billion trillion stars to our count, increasing the total from 200 billion trillion to potentially 220 billion trillion or more. These stars experience a different existence than their galactic counterparts. Without a galaxy's gravitational structure to orbit, they drift relatively freely through space, separated from any other stars by vast distances. If such a star had planets, which is possible, those planets would have an unimaginably dark night sky. No band of the Milky Way stretching overhead, no nearby stars forming familiar constellations, just a few distant galaxies, faint smudges of light separated by endless darkness. It would be, in a very real sense, the loneliest place in the universe. And yet tens of billions of trillions of stars might exist in these conditions, cast out from their galactic homes to wander the void. So we've established the number, 200 billion trillion stars, give or take. We've explored the uncertainty in that number. We've tried to comprehend its magnitude. We've examined the diversity of stars and where they're located. But now let's address a different kind of question. What does this number mean? Why does it matter that there are 200 billion trillion stars rather than, say, 1 trillion or 1 quadrillion? One answer is about perspective and possibility. Understanding the sheer number of stars in the universe fundamentally changes how we see our place in it and what might exist beyond Earth. Every star is a sun, a potential center of a solar system, a possible home to worlds we can barely imagine. 200 billion trillion opportunities for planetary systems to exist. And we now know, thanks to observations from the Kepler Space Telescope, the Transiting Exoplanet Survey satellite, and ground-based planet hunting programs, that planets are common, not rare, not exceptional, common. Most stars have planets. The current data suggests that on average, every star has at least one planet, probably more. Some stars have 7 or 8 known planets. Our own solar system has 8 major planets, 5 dwarf planets, and countless smaller bodies. If we conservatively estimate 1 planet per star, that's 200 billion trillion planets in the observable universe. 200 billion trillion worlds scattered across space. Many of those planets are gas giants, massive worlds like Jupiter and Saturn with no solid surface. These planets have crushing atmospheres of hydrogen, helium, methane, and ammonia. Some orbit so close to their stars that their atmospheres are being boiled away. Others orbit so far out that they're frozen solid, cold and dark, and utterly inhospitable. But some fraction of those 200 billion trillion planets are rocky worlds like Earth, terrestrial planets with solid surfaces made primarily of rock and metal. And some fraction of those rocky worlds orbit in what astronomers call the habitable zone or Goldilocks zone. The habitable zone is the range of distances from a star where the temperature is just right for liquid water to exist on a planet's surface. Not so close that water boils away, not so far that water freezes solid. Just right for liquid water, the essential ingredient for life as we know it. For a Sun-like G-type star, The habitable zone extends from about 0.9 to 1.5 astronomical units from the star. Earth orbits at 1 astronomical unit, right in the middle. Venus orbits at 0.72 AU, too close, resulting in a runaway greenhouse effect. Mars orbits at 1.52 AU, near the outer edge. Too cold now, though it might have been warmer billions of years ago. For smaller, cooler red dwarf stars, the habitable zone is much closer, perhaps 0.1 to 0.2 AU. For larger, hotter stars, it's farther out. But every star has a habitable zone, a region where conditions might be right for life. Recent studies of exoplanets suggest that perhaps 5 to 20% of Sun-like stars have an Earth-sized planet in the habitable zone. Let's be conservative and say 10%. If 10% of all stars have a rocky planet in the habitable zone, that's 20 billion trillion potentially habitable worlds, 20 quadrillion planets where liquid water could exist, where the temperature might be comfortable, where an atmosphere could persist, where life, as we understand it, could potentially emerge and evolve. Think about that number, 20 billion trillion potentially habitable planets. Now, we don't know how likely life is to emerge on any given habitable planet. The origin of life is one of the deepest mysteries in science. We know it happened at least once, on Earth. But we don't know if Earth was extraordinarily lucky or if life is nearly inevitable given the right conditions. Life appeared on Earth relatively quickly in geological terms. Earth formed 4.54 billion years ago. The earliest evidence for life, in the form of chemical signatures in ancient rocks, dates to about 3.8 billion years ago. That's only about 700 million years after Earth formed. Given that the planet was still being heavily bombarded by asteroids during much of that time, life emerged remarkably fast. This seems to suggest that given the right chemistry, the right energy sources, and liquid water, life arises readily, but we have a sample size of 1, which is statistically meaningless. It's possible that Earth was incredibly lucky, that the origin of life requires such a specific and improbable series of chemical reactions that it might happen only once in a trillion planets. Or it's possible that life is nearly inevitable, that, given the right conditions, chemistry naturally organizes itself into self-replicating systems that we recognize as life. We simply don't know yet. But even if we assume the probability is very low, the sheer number of opportunities is staggering. If the chance of life emerging on any given habitable planet is 1 in 1 million, that's still 20 billion life-bearing worlds. 20 quintillion planets with life, even if it's just simple microbial life. If the probability is 1 in 1 billion, that's still 20 billion planets with life. If it's 1 in 1 trillion, there are still 20 million life-bearing worlds in the observable universe, even at odds of 1 in 1 trillion, which seems unreasonably pessimistic given how quickly life appeared on Earth. There would be millions of planets with life scattered across the cosmos. And we're not just talking about microbial life, though that would be profound enough. On Earth, life remained single-celled for about 2 billion years before the first multicellular organisms appeared. Complex animals didn't arise until the Ediacaran and Cambrian periods, about 600 to 540 million years ago. So complex life might be rarer than simple life. It might require not just the right chemistry, but also billions of years of stable conditions and several unlikely evolutionary innovations. Things like the development of the eukaryotic cell, the origin of photosynthesis, the oxygenation of the atmosphere, and the evolution of multicellularity. Each of these was a major transition that took enormous time. But again, even if complex life is 1,000,000 times rarer than simple life, the vast numbers mean there could still be trillions of worlds with complex organisms. And some tiny fraction of those worlds might develop intelligent life and technology. Intelligence might be the rarest outcome of all. On Earth, human-level intelligence emerged very recently, only within the last few 100,000 years. That's about 0.01% of Earth's history. For 4.5 billion years, Earth existed without intelligent life capable of building civilizations and technologies. Intelligence might require very specific evolutionary pressures: tool use, language, social cooperation, abstract reasoning. All these had to evolve in the right sequence. And technological civilization has existed for only about 10,000 years. Agriculture and writing, radio communication and spaceflight have existed for only about 100 years. That's an eye blink, a fraction of a percent of Earth's history. So technological civilizations might be extraordinarily rare. But with 20 billion trillion potentially habitable planets, even extraordinarily rare events happen. The famous Drake equation, proposed by astronomer Frank Drake in 1961, attempts to estimate the number of technological civilizations in our galaxy. It multiplies together several factors: the rate of star formation in the galaxy, the fraction of stars with planets, the number of planets per star that could support life, the fraction where life actually emerges, the fraction where life develops intelligence, the fraction where intelligence develops technology capable of interstellar communication, and the average lifetime of such technological civilizations. We're getting pretty good at estimating the first few factors. We know star formation rates reasonably well. We know most stars have planets. We're learning about habitable zone planets. But the later factors, especially those involving life, intelligence, and civilization lifetimes, are almost completely unknown. We have exactly one example, us, which makes estimating probabilities impossible. Depending on what values you plug into the Drake equation, you can get answers ranging from "we're alone in the galaxy" to "there are millions of civilizations." Conservative estimates, assuming life and intelligence are very rare, suggest there might be only a handful of technological civilizations in the Milky Way at any given time. Optimistic estimates suggest there could be thousands or millions. The truth is, we simply don't know. But here's what we do know. Our galaxy is just one of 2 trillion galaxies. If there are even just 10 technological civilizations per galaxy on average, that's 20 trillion civilizations in the observable universe. If it's 100 per galaxy, that's 200 trillion civilizations. The numbers quickly become enormous. Of course, this assumes life follows similar patterns everywhere. It assumes evolution generally leads to intelligence and technology given enough time. It assumes civilizations develop radio communication or other detectable signatures. All of these assumptions could be wrong. Evolution on other worlds might take completely different paths. Intelligence might emerge in forms we wouldn't recognize or communicate with, methods we can't detect. Technology might develop in ways we can't imagine, but the fundamental point remains. The existence of 200 billion trillion stars creates an almost unlimited number of opportunities. Opportunities for planets, opportunities for chemistry, opportunities for life, opportunities for intelligence, opportunities for civilizations. Even if each individual opportunity has a vanishingly small probability of success, when you multiply by 200 billion trillion, the result is significant. There are likely countless worlds with life out there, worlds where evolution has taken different paths, creating organisms unlike anything on Earth, worlds where intelligent beings might be asking the same questions we're asking, looking up at their night sky, counting their stars, wondering if they're alone. Some of those civilizations might be far more advanced than us, having had millions or billions of years more time to develop. They might have technologies we can barely conceive of. They might have solved problems we haven't even recognized yet. Others might be less advanced, still in their equivalent of our Stone Age or Bronze Age. Still others might have risen and fallen, leaving only ruins and faint signals scattered across their solar systems. The universe might be full of life at various stages of development, scattered across those 200 billion trillion stellar systems. And yet, despite the probabilities suggesting we're not alone, we haven't found anyone yet. This is the Fermi paradox, named after physicist Enrico Fermi. If intelligent life and technological civilizations are common, where is everybody? Why haven't we detected any signals? Why haven't we been visited? There are many proposed solutions. Perhaps space is just too vast and civilizations too far apart. The nearest civilization might be thousands or millions of light years away, too distant for communication. Perhaps technological civilizations don't last long. They might destroy themselves through war, environmental collapse, or technological disasters. Perhaps intelligence is far rarer than we think. Perhaps we're among the first civilizations to arise. Perhaps advanced civilizations deliberately avoid contact with less developed ones. Perhaps they use communication methods we haven't discovered yet. Perhaps they're here but hiding. Or perhaps we really are alone, the only technological civilization in the observable universe. That seems unlikely given the numbers, but it's possible. We don't know. But the search continues. SETI, the search for extraterrestrial intelligence, monitors the skies for radio signals from other civilizations. We send probes to other planets in our solar system, looking for signs of past or present microbial life. We study exoplanets, trying to detect biosignatures in their atmospheres. The search has found nothing conclusive yet, but we've barely started looking. We've examined only a tiny fraction of the observable universe. We've studied only a handful of the billions of potentially habitable planets. The absence of evidence is not evidence of absence, especially when we've barely begun to look. The fact that there are 200 billion trillion stars means the search space is almost incomprehensibly vast. We could search for centuries and still have examined only a minuscule fraction of possible locations. But every star we examine, every planet we study, every signal we analyze brings us one step closer to answering one of humanity's deepest questions. Are we alone? The number of stars suggests the answer is probably no. Somewhere out there, among those 200 billion trillion suns, there are almost certainly other worlds, other life, perhaps other minds, contemplating the same vastness we're contemplating. We just haven't found each other yet. The distances are too vast, the universe too large, the search too new, but the possibility exists, made real by the sheer abundance of stars. 200 billion trillion opportunities for something extraordinary to happen. And that changes everything about how we see ourselves and our place in the cosmos. 200 billion trillion opportunities for worlds to exist. We know now that planets are common. Observations from the Kepler Space Telescope and other planet-hunting missions have revealed that most stars have planets. The average is probably at least one planet per star, and likely more. If we conservatively estimate one planet per star, that's 200 billion trillion planets in the observable universe. Many of those planets are gas giants, Jupiter-like worlds inhospitable to life as we know it. But even if only 1% of planets are rocky, Earth-like worlds in their star's habitable zone, that's still 2 billion trillion potentially habitable planets. 2 billion trillion places where liquid water could exist, where chemistry could become biology, where life could emerge. Now, we don't know how likely life is to emerge on any given habitable planet. The origin of life might be extremely improbable, a freak accident of chemistry that happened once in the entire observable universe. Or it might be nearly inevitable, given the right conditions. We simply don't know. We have exactly one example, Earth, which is not enough data to draw conclusions. But even if the probability of life emerging on any given habitable planet is extremely low, the sheer number of opportunities is staggering. If the chance is 1 in 1 million, that's still 2 billion planets with life. If it's 1 in 1 billion, that's still 2 billion planets with life in the observable universe. Even if the odds are 1 in 1 trillion, which seems unreasonably pessimistic given how quickly life appeared on Earth, that's still 2 million planets with life. And we're not just talking about microbial life, though that would be profound enough. Some fraction of those life-bearing worlds might develop complex life. Some might develop intelligence. Some might develop technological civilizations capable of asking the same questions we're asking. The famous Drake equation attempts to estimate the number of communicative civilizations in our galaxy by multiplying various probabilities together. The rate of star formation, the fraction with planets, the number of habitable planets per star, the fraction where life emerges, the fraction where intelligence develops, the fraction that develops technology capable of communication, and how long such civilizations last. We don't know most of these values with any precision, but given the sheer number of stars, even conservative estimates suggest there should be at least dozens, probably hundreds or thousands, of technological civilizations in our galaxy alone. Extrapolate that to 2 trillion galaxies, and the number of civilizations in the observable universe could be in the billions or trillions. Of course, this assumes life follows similar patterns everywhere, which might not be true, and it assumes that intelligent, technological civilizations are a natural outcome of evolution, which we can't confirm. But the point is that the enormous number of stars creates an enormous number of opportunities. The universe is not sterile. It's not empty. It's a vast arena full of potential. There's another implication of this number that's worth considering. The fact that there are 200 billion trillion stars means the universe is fundamentally a place of abundance, not scarcity. We live on one planet, orbiting one star in one galaxy. That galaxy contains 100 billion to 400 billion other stars, and that galaxy is one of 2 trillion galaxies. In this context, our Sun is not special. It's not unique. It's not even particularly remarkable. It's one star among 200 billion trillion, a middle-aged yellow dwarf of average size and luminosity. In the grand scheme of things, our Sun is utterly ordinary, and yet it's the center of our world. It's the source of the energy that powers life on Earth. It's the reason we exist. This creates a kind of cognitive dissonance. On one hand, we're insignificant, one planet among perhaps 200 billion trillion planets, orbiting one star among 200 billion trillion stars. On the other hand, we're here. We're conscious. We can contemplate these numbers. We can ask questions about our place in the cosmos. The fact that we can count the stars, even approximately, is itself remarkable. No other species on Earth, as far as we know, can do this. We've developed mathematics, built telescopes, launched satellites, and figured out how to count objects separated from us by billions of light years. That ability, that capacity for abstract thought and scientific inquiry, is rare. It might even be unique in our galaxy or our galactic neighborhood. So, while we're physically insignificant, one planet among countless trillions, we might be significant in another way. We might be among the rare instances where the universe has become conscious of itself, where matter has organized itself into brains capable of understanding the cosmos. This is sometimes called the anthropic principle, the observation that we can only observe the universe from a position where observers like us can exist. But it goes deeper than that. The universe is not just observable, it's comprehensible. The laws of physics are mathematical. They follow patterns we can understand. The universe didn't have to be this way. It could have been chaotic, lawless, impossible to understand, but it's not. And we, a species evolved on one tiny planet, have figured out much of how it works. We know why stars shine. We know how galaxies form. We know the age of the universe. We can count the stars, at least approximately. That's astonishing. So yes, there are 200 billion trillion stars, and in that context we're vanishingly small, but we're also capable of knowing there are 200 billion trillion stars. And that knowledge, that understanding, is itself a kind of significance. Let's bring this back to something you can directly experience. Tonight, if the sky is clear, go outside and look up. Find a dark location away from city lights if you can. Let your eyes adjust to the darkness. You'll see a few thousand stars, maybe more if conditions are perfect. Now remember that each of those stars is part of a count that extends beyond anything your mind can truly grasp. For every star you can see, there are approximately 70 billion trillion you cannot see. 70 billion trillion stars for each visible point of light in the night sky. That band of light stretching across the sky, the Milky Way, is light from billions of stars too distant and faint to see individually. You're looking at a slice of our galaxy, a cross-section of the disk containing the spiral arms. Our galaxy is approximately 100,000 light-years across, and we're about 26,000 light-years from its center. When you look at the Milky Way, you're seeing across tens of thousands of light-years of space through billions of stars. But our entire galaxy, vast as it is only one of 2 trillion. Most galaxies are too distant to see with the naked eye. Andromeda, our nearest large galactic neighbor, is barely visible as a faint smudge even under dark skies. It's 2.5 million light-years away. The light you see from Andromeda left that galaxy 2.5 million years ago, when early human ancestors were just beginning to use stone tools. And Andromeda, clearly visible with binoculars, is one of the closest galaxies to us. Most of the 2 trillion galaxies are billions of light-years away, completely invisible without large telescopes. The light from the most distant galaxies we can see has been traveling for over 13 billion years. It left those galaxies when the universe was only a few 100 million years old, long before the Sun or Earth existed. We're seeing them not as they are now, but as they were in the universe's distant past. Those galaxies have likely evolved, merged with other galaxies, formed new generations of stars. Some of the stars we're seeing in those distant galaxies have certainly died by now. They've gone supernova, created neutron stars or black holes, and scattered their matter back into space. But their light is still traveling toward us, carrying information about the universe's early history. This means that when we count 200 billion trillion stars, we're counting across both space and time. Some of those stars exist now, in the universe's present moment. Others existed in the past and have since died, but their light is still traveling through space, and we count them in our census. And still others are being born right now, condensing out of giant molecular clouds, igniting their nuclear furnaces for the first time. The count is dynamic, constantly changing. Every second, somewhere in the observable universe, stars are dying. Somewhere else, new stars are being born. The total number fluctuates, but the order of magnitude stays roughly the same. 200 billion trillion is the current snapshot, our best estimate of how many stars exist in the observable universe at this moment in cosmic history. So what happens to this number in the future? Will there always be 200 billion trillion stars? The answer is no. The universe is evolving, and the stellar population will change dramatically over time. Currently, stars are still being born at a significant rate across the universe. In the Milky Way, We form about 1 to 2 new stars per year on average. That might not sound like much, but multiply it by 2 trillion galaxies, and you get several trillion new stars being born every year across the observable universe. In absolute terms, that's an enormous number of new stars. But as a fraction of the existing 200 billion trillion stars, it's tiny. It would take hundreds of billions of years at the current rate to double the stellar population. And that's never going to happen because the rate of star formation is actually decreasing. Star formation requires gas, specifically cold hydrogen and helium, that can collapse under gravity to form new stars. Over time, this gas gets locked up in several ways. Some forms stars and never returns to the interstellar medium. Some gets locked up in stellar remnants, white dwarfs, neutron stars, and black holes. Some gets heated to such high temperatures by supernova explosions and supermassive black holes that it can't cool down and collapse. And some gets ejected from galaxies entirely by powerful galactic winds. The rate of star formation in the universe peaked about 10 to 11 billion years ago, roughly 3 billion years after the Big Bang. At that time, the universe was forming stars about 10 to 30 times faster than it does today. That was the era of peak star formation, when most of the stars that exist today were born. Since then, the rate has been steadily declining. Currently, the universe is forming stars at only about 3 to 5% of its historical peak rate. And that rate will continue to drop. Projections based on our understanding of galactic evolution suggest that star formation will decline exponentially over the next trillion years. In about 1 trillion years, most galaxies will have exhausted their star-forming gas. The last generation of stars will be born, and after that, no new stars will ever form. The universe will contain only the stars that already exist, slowly burning through their remaining fuel. But stars don't last forever either. They eventually exhaust their fuel and die. The most massive stars live only a few million years before exploding as supernovae. These stars are already gone. Any O-type star that formed more than 10 million years ago has already died. Medium-sized stars like our Sun live about 10 billion years. The Sun has about 5 billion years left. Stars similar to the Sun that formed in the early universe 13 billion years ago are now reaching the ends of their lives and becoming white dwarfs. But the smallest stars, the red dwarfs that make up 3/4 of all stars, can live for trillions of years. The smallest red dwarfs might live for 10 to 20 trillion years, burning their hydrogen fuel so slowly that they'll outlast almost everything else in the universe. Not a single red dwarf that has ever been born has died yet. Every red dwarf that formed in the early universe is still on the main sequence, still burning hydrogen, still shining. They'll continue for trillions of years into the future. This means the number of stars in the universe will decline over time, but very slowly at first. For the next few 100 billion years, the number will remain roughly constant as new star formation approximately balances stellar deaths. But after about 1 trillion years, with star formation having ceased, the number will begin to decline noticeably. First, all the remaining massive stars will die. This happens relatively quickly because by that point, only stars less than about 1 solar mass will still exist, and they live tens to hundreds of billions of years. Then the Sun-like stars will die, shrinking the stellar population further. Eventually, after about 10 trillion years, the last of the Sun-like stars will exhaust their fuel and become white dwarfs. Only red dwarfs will remain, the last stars burning in an increasingly dark universe. For perhaps another 10 trillion years, these red dwarfs will continue to shine. The universe will be dim and cold, with only these faint red embers providing any light at all. Galaxies will be dark, except for the faint glow of billions of red dwarfs, and the cooling white dwarfs left behind by dead stars. And then, in about 20 to 100 trillion years, even the longest-lived red dwarfs will exhaust their fuel. They'll slowly contract and cool, becoming white dwarfs themselves. The last star in the universe will flicker out. After that, the universe will enter what's called the degenerate era. No stars will exist anywhere. The only remnants of the stelliferous era, the age of stars, will be cooling white dwarfs, neutron stars, and black holes. White dwarfs will slowly radiate away their residual heat, taking quadrillions of years to cool from white-hot to red to brown to eventually black. But the universe isn't old enough yet for any white dwarf to have cooled completely. Every white dwarf in existence is still glowing. In about 10 to the power of 15 years, that's a quadrillion years, white dwarfs will have cooled to the point where they emit almost no light. The universe will be almost completely dark. Only the faint heat radiation from cooling stellar remnants will exist. But even that's not the end. Given enough time, even the most stable objects decay. Stephen Hawking showed that black holes slowly evaporate through a quantum process called Hawking radiation. Small black holes evaporate quickly, in fractions of a second, but massive black holes evaporate very, very slowly. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate completely. The supermassive black holes at the centers of galaxies, with billions of times the Sun's mass, will take about 10 to the power of 100 years to evaporate. That's a Google years. One followed by 100 zeros. A time span so long, it's almost meaningless. After all the black holes have evaporated, the universe will contain nothing but elementary particles, photons, electrons, positrons, and neutrinos, drifting apart as space continues to expand. No stars, no galaxies, no planets, no structures of any kind. Just particles, increasingly isolated in an ever-expanding void. This is the heat death of the universe, the ultimate fate according to our current understanding of physics. Maximum entropy, thermal equilibrium, no free energy available to do work, nothing interesting can ever happen again. It's a bleak picture of the far future, but it's also unimaginably distant. The time until the last star dies is about 10 trillion years. That's 725 times longer than the current age of the universe. To put that in perspective, the ratio of 10 trillion years to the current age of the universe is the same as the ratio of the current age of the universe to about 19 million years. 19 million years ago, our human ancestors didn't exist, not even close. The ancestors of humans and chimpanzees hadn't diverged yet. The universe has aged that much, proportionally, 725 times over. That's how long stars will continue to exist. We're living in the universe's early days, cosmologically speaking. The stelliferous era has only just begun relative to how long it will last. Most of cosmic history, the vast majority of it, will be the slow decline and death of stars. The universe will spend far more time in darkness than in light. But right now, in this cosmic moment, there are 200 billion trillion stars lighting up the void. Galaxies are still bright and active. Star formation is still happening. New stars are still being born, while old stars die and scatter their elements. This is, in a very real sense, the best time to be alive in the universe. Billions of years from now, long after humanity is gone, the universe will be darker and emptier. Trillions of years from now, it will be unrecognizably different. But right now, we exist during the golden age of stars. And we're here to count them and marvel at them. Currently, stars are still being born at a rate of roughly several per year in a typical galaxy. In the Milky Way, we form about 1 to 2 new stars per year on average. Multiply that by 2 trillion galaxies, and we get several trillion new stars being born every year across the observable universe. That sounds like a lot, and it is in absolute terms. But as a fraction of the existing 200 billion trillion stars, it's tiny. It would take hundreds of billions of years at that rate to double the stellar population. And the rate of star formation is actually decreasing. Star formation requires gas, specifically hydrogen and helium, that can collapse under gravity to form new stars. Over time, this gas gets used up. It either forms stars, gets locked up in the remnants of dead stars, or gets heated to such high temperatures by black holes and supernovae that it can't collapse to form new stars. The rate of star formation in the universe peaked about 10 billion years ago. It's been declining ever since. Currently, the universe is forming stars at only about 3% of its historical peak rate, and that rate will continue to drop. In about 1 trillion years, give or take, star formation in the universe will essentially cease. All the available gas will have been used up. The last generation of stars will be born, and after that, no new stars will ever form. The universe will contain only the stars that already exist, slowly burning through their fuel. But stars don't last forever. They use up their nuclear fuel and die. The most massive stars live only a few million years before exploding as supernovae. Medium-sized stars like our Sun live about 10 billion years. Small red dwarfs, the most common type of star, can live for trillions of years because they burn their fuel so slowly. As time passes, the number of stars in the universe will decline. First, all the massive bright stars will die. This has already happened for many of the earliest stars. Then the medium-sized stars will die. Our Sun has about 5 billion years left. Eventually, only red dwarfs will remain, faint embers slowly burning through the last of the universe's hydrogen. In about 10 trillion years, even the longest-lived red dwarfs will start to die. By about 100 trillion years from now, the last star in the universe will flicker out. After that, the universe will enter what's called the degenerate era. No stars will exist. The only luminous objects will be the slowly cooling remnants of dead stars, white dwarfs, and neutron stars, emitting faint thermal radiation. Black holes will persist, but they emit no light. The universe will be dark, cold, and essentially dead. But even that's not the end. Given enough time, even black holes evaporate through a process called Hawking radiation. The largest black holes, the supermassive black holes at the centers of galaxies, will take about 10 to the power of 100 years to evaporate. That's a 1 followed by 100 zeros, a Google years. After that, the universe will contain nothing but a thin soup of elementary particles, drifting apart as space continues to expand. No stars, no galaxies, no structures of any kind. Just particles, increasingly isolated in an ever-expanding void. This future, called the heat death of the universe, is the ultimate fate of the cosmos, according to our current understanding. It's a bleak picture, but it's also unimaginably far in the future. The time between now and the last star dying is about 10 trillion years. That's 725 times longer than the current age of the universe. We're living in the universe's early days, cosmologically speaking. The stelliferous era, the age of stars, has only just begun. Most of cosmic history will be the slow decline and death of stars, a process that will take thousands of times longer than the universe's current age. So when we count 200 billion trillion stars, we're counting the population during a brief and special period of cosmic history. The time when star formation is still happening, when the universe is young and vibrant, when galaxies are still bright and active. This is, in a very real sense, the best time to be alive in the universe. Billions of years from now, Long after humanity is gone, the universe will be darker and emptier. Trillions of years from now, it will be unrecognizably different. But right now, in this cosmic moment, there are 200 billion trillion stars lighting up the darkness, and we're here to count them. There's one more implication of this number that we need to discuss. The fact that we can count stars at all, that we can look out into the cosmos and estimate how many exist, represents one of humanity's greatest intellectual achievements. For most of human history, the stars were a mystery. Ancient peoples saw them as lights, affixed to a celestial sphere, holes in the fabric of the sky, or the spirits of the dead. They had no concept of what stars actually were, or how far away they were. The idea that stars are other suns, distant and vastly far away, was proposed by ancient Greek philosophers, but couldn't be proven. It wasn't until the 19th century that astronomers finally measured the distance to the nearest stars using parallax. The apparent shift in a star's position as Earth orbits the Sunday, those measurements revealed that stars are trillions of miles away, far beyond anything humans had previously imagined. Understanding what stars are, balls of gas undergoing nuclear fusion, came even later in the early 20th century. Einstein's theories of relativity, combined with quantum mechanics, finally explained how stars could shine for billions of years without running out of fuel. And the realization that there are other galaxies beyond our own, each containing billions of stars, only came in the 1920s, when Edwin Hubble measured the distance to Andromeda and proved it was far outside the Milky Way. So the knowledge that there are 200 billion trillion stars is very recent in human history. Our great-grandparents lived in a time when astronomers thought the Milky Way was the entire universe. Our grandparents lived in a time when we didn't know other galaxies contained stars like ours. Our parents lived in a time when we thought there might be only 100 billion galaxies, not 2 trillion. This count, this number, represents the cutting edge of human knowledge. It's the result of thousands of scientists over decades, building increasingly powerful telescopes, developing new observation techniques, launching satellites into orbit, and carefully analyzing the data. Every time we improve our instruments, we see more. Every time we develop a new technique, we discover something unexpected. The number 200 billion trillion is not final. It's our current best estimate based on what we can observe with our present technology. As our technology improves, the number might change. We might discover more faint dwarf galaxies, increasing the total. We might find that some galaxies contain more stars than we thought. We might detect intracluster stars we previously missed. Or we might find that some of our assumptions were wrong and the number is actually lower. The point is that we're still learning. We're still exploring. We're still pushing the boundaries of what we can observe and understand. And that process, that journey of discovery, is ongoing. Every generation sees farther and more clearly than the last. Every generation adds to our understanding of the cosmos. And every generation is astonished by what they find. Our generation's astonishment is the sheer scale of the universe. 200 billion trillion stars, 2 trillion galaxies. A cosmos so vast that light takes billions of years to cross it. A universe so old that entire stellar civilizations could have risen and fallen long before our sun was even born. This is the universe we live in. Not a small, cozy cosmos with Earth at its center. Not a static, unchanging realm. But a vast, ancient, evolving universe full of wonders we're only beginning to understand. So here's what I want you to take away from all of this. When you look up at the night sky and see a few thousand stars, remember that you're seeing an infinitesimally small sample of what's out there. For every visible star, there are 70 billion trillion more beyond your sight. When you hear that number, 200 billion trillion, Don't let it become just another statistic. Try to feel the weight of it. Try to imagine what it means. 200 billion trillion separate nuclear furnaces, each one unique, each one with its own history and fate. 200 billion trillion potential centers of solar systems. 200 billion trillion opportunities for worlds to exist. It's a number so large it defies comprehension, and yet it's real. Those stars exist. They're out there right now, burning, shining, evolving, dying. They're separated from us by unimaginable distances, but they're part of the same universe we inhabit, made of the same matter, governed by the same laws of physics. And we, unlikely as it seems, are able to count them. We're able to look across billions of light years and estimate how many there are. We're able to understand what they are and how they work. That ability, that understanding, is humanity's gift. We're a species that looks at the night sky and asks questions. We're not content to wonder passively. We build telescopes. We do the math. We figure it out. And what we've figured out is this: the universe is larger, older, more complex, and more full of wonders than anyone in previous generations could have imagined. There are 200 billion trillion stars in the observable universe, and every single one is a story waiting to be told. Most of those stories we'll never know. Most of those stars we'll never see, but we know they're there. And knowing that, understanding our place in this vast cosmic tapestry, changes us. It makes us smaller and yet somehow more significant. Smaller because we're just one species on one planet, orbiting one star among 200 billion trillion. More significant because we're capable of understanding that fact. We're the universe looking at itself. Matter organized in such a way that it can contemplate its own existence. That's rare. That might even be unique. And it's worth celebrating. So tonight, if you can, go outside, look up at the stars, and remember what you now know. Those few thousand visible stars are just the beginning. Beyond them, invisible but real, are 200 billion trillion more, each one a sun, each one a nuclear furnace, each one a small piece of the vast, ancient, incomprehensibly large universe we call home. And you, standing on your tiny planet, looking up at the night sky, are part of that universe. You're made of star stuff, atoms forged in the hearts of previous generations of stars. You're a way for the cosmos to know itself. This is not poetic exaggeration. It's literally true. For 13.8 billion years, the universe existed without consciousness, as far as we know, just matter and energy following physical laws. Stars formed and died. Galaxies swirled through space. Planets orbited suns. But none of it was witnessed or understood. Then, on at least one planet, and probably many more scattered across those 200 billion trillion stellar systems, matter organized itself into life. Simple chemicals became complex organic molecules. Those molecules became self-replicating systems. Those systems evolved, over billions of years, into increasingly complex organisms. And eventually, some of those organisms developed consciousness, the ability to perceive, to think, to understand. On Earth, that process took 4 billion years. From the first simple cells, to fish, to amphibians, to reptiles, to mammals, to primates, to humans. And now we're here, capable of abstract thought and scientific reasoning, capable of building telescopes and satellites and mathematical models, capable of looking at the night sky and not just seeing lights, but understanding that we're seeing distant suns, each one potentially hosting worlds like our own. This is what makes the number 200 billion trillion more than just a statistic. It represents opportunity. Opportunity for planets to form. Opportunity for life to emerge. Opportunity for consciousness to develop. opportunity for the universe to become aware of itself. And that awareness, that understanding, is precious beyond measure. It's easy to feel insignificant when confronted with these vast numbers, 200 billion trillion stars, and you're just one organism on one planet orbiting one of them. Your life is measured in decades, while the universe is measured in billions of years. You occupy a space a few feet tall, while the universe extends for billions of light years. By any objective measure, you're utterly insignificant in the cosmic scheme. But that's not the whole story. Yes, you're physically tiny and temporally brief, but you're also capable of comprehending the vastness that dwarfs you. You can count the stars, at least approximately. You can understand what they are and how they work. You can contemplate distances and timescales that extend far beyond your direct experience. That ability to transcend your physical limitations through thought is what makes you significant. You're not important because of your size or strength or lifespan. You're important because you can understand, because you can ask questions about reality and find answers, because you're conscious and curious. And that consciousness, that curiosity, might be rare in the universe. We don't know yet, but it's certainly not common. Out of all the matter in the observable universe, an almost infinitesimally small fraction has organized itself into thinking beings. Most matter is in stars, mindlessly fusing hydrogen into helium. Most is in dead remnants, white dwarfs and neutron stars and black holes. Most is in gas clouds drifting through space. Most is in rocks and ice, inert and unchanging. Only a tiny, tiny fraction has become alive, and an even tinier fraction has become conscious. You're part of that rare fraction. That alone makes you significant, regardless of your physical size. The universe spent 13.8 billion years creating the conditions necessary for you to exist. First, it had to create the first generation of stars to forge heavy elements. Then those stars had to die and scatter those elements into space. Then new stars had to form from that enriched gas. Then planets had to form around those stars. Then the right conditions had to exist on at least one of those planets for life to emerge. Then that life had to survive and evolve for billions of years. And finally, after all that, you arrived. You're the product of the entire history of the universe. Every step was necessary. Skip any of them, and you wouldn't be here. So when you look up at those 200 billion trillion stars, remember that you're connected to them, not just made of the same elements, though that's true, not just governed by the same physical laws, though that's also true, but connected through the vast chain of causality that links the Big Bang to this present moment. Those stars created the elements in your body. Their light warms your planet. Their gravity shapes the structure of galaxies, and their existence makes possible the emergence of life and consciousness. Without stars, the universe would be dark, cold, and dead. Just hydrogen and helium drifting through endless space. No planets, no life, no observers. Stars are what make the universe interesting. They're the furnaces that create complexity. They're the engines that drive cosmic evolution. And there are 200 billion trillion of them, ensuring that the universe is full of opportunity and possibility. Some of those stars have already died. Some are being born right now. Some will continue burning for trillions of years into the future. Each one is unique, with its own mass, temperature, composition, and fate. Each one is a small part of a vast cosmic ecosystem. And you, through science and mathematics and careful observation, can understand all of this. You can know how many stars there are, approximately. You can understand how they form and evolve and die. You can comprehend the timescales and distances involved. That understanding is humanity's greatest achievement, not our technology, though that's impressive, Not our art or music or literature, though those are wonderful, but our ability to figure out how the universe works, to look at the night sky and decode its secrets, to measure the unmeasurable and comprehend the incomprehensible. That's what makes us special as a species. We're curious. We ask questions. We seek answers. And we find them. Not all of them, not yet. There's still so much we don't know. We don't know if we're alone in the universe. We don't know exactly how life began. We don't know what dark matter is or why the universe's expansion is accelerating. We don't know what happened before the Big Bang, if that question even makes sense. But we keep looking. We keep asking. We keep building better telescopes and conducting better experiments and developing better theories. Each generation adds to our understanding. Each discovery opens new questions. The journey of discovery never ends. And that's beautiful in its own way. We'll probably never know everything. The universe is too large, too complex, too strange. But we'll keep learning. We'll keep pushing back the boundaries of ignorance. We'll keep counting the stars and measuring the cosmos, because that's what conscious beings do. We seek to understand.